Hello, welcome back to my series of videos from my book, The Effect, which can be found at theeffectbook.net with links to purchase if you're interested, or you can read the whole thing for free. In this video, we're going to be talking about conditional distributions, which is another way of thinking about controlling for a variable. You might have heard that term before, controlling for a variable or adjusting for something. So what exactly does that mean? So let's see what we've gone through so far. So we started with the idea of distributions. We know how a variable can be distributed in its sample, right? And we talked about what proportion of the time it takes one value or another value or whatever. We can summarize that distribution by taking something like the mean. What is the mean of that variable? Then we talked about conditional distributions, and that is if I look at the different values of one variable, how does the distribution of the other one change? So for example, the distribution of gender might be very different, conditional on knowing that somebody's name is Sarah versus conditional on knowing that their name is Chris. The distribution of gender would probably be very different in those two scenarios. So that can tell us about the relationship between two variables. So that shows me that there's a positive relationship between, say, gender and name, or at least being named Sarah, because if I learn that your name is Sarah, that increases the probability that I believe that you are female. So what about other things, right? So when we have a prediction, when we have a distribution, especially if we're talking about something like a conditional mean, conditional on your body mass index being 22, I might think that there is a 20% chance that you take vitamin E or something like that. That's a conditional mean. Well, there's going to be a part that I've explained about that variable and a part that I have not, the residual. So let's say, for example, we're talking about, I'm a professor, I'm a college professor, and I also drink coffee. So you might say, okay, well, given that you're a college professor, conditional on being a college professor, how much coffee would I expect you to drink? Maybe the average amount of coffee that college professors drink is, let's say, 2.3 cups a day of coffee. Right? Now, if I drink 3 cups a day of coffee, well, what do we got there? Well, you've explained 2.3 of my cups, right? You would have expected that as a professor, knowing that I'm a professor, that I would drink 2.3 cups of coffee per day. But I, in fact, drink 3 cups. So there's a difference of 0.7 between the 2.3 cups of coffee that you expected me to drink and the 3 cups of coffee that I actually do. So we have the explained part and the unexplained part, which is the difference between what you expected and what you actually saw. Now this sounds, like a bummer, right? You're not going to be able to predict exactly how much coffee every individual drinks based on only that means. But what we do get is that this unexplained part, this residual, there's something special about it because that's the part of coffee drinking that is just unique to me that doesn't have anything to do with me being a professor. If you were just looking at my professor-based coffee drinking, you'd say, 2.3 cups. But I'm not quite there, which means that there's some other sort of magic sauce going on between 2.3 and 3. That is the part of coffee drinking that is not explained by the fact that I'm a professor. It must be something else going on, which turns out to be very important. Because what about this? Let's go one step further, okay? Let's say that that you want to know not the relationship between coffee drinking and being a professor, but let's say coffee drinking and, having brown hair, let's say, right? So maybe let's say that people who have brown hair are more likely to be professors. And so if you looked in the data and you said, hey, it looks like people who drink brown hair are really likely to drink a lot of coffee, right? Maybe that's what you find in the data. Somebody else might come to you and say, well, yeah, sure, okay, yeah, they drink more coffee, but that's probably just because they're more likely to be professors, and professors drink a lot of coffee, right? You say, well, okay, yeah, maybe that's true. I need to account for that. Well, let's go back to that residual. Well, that 0.7, the difference between the 2.3 and the 3 that I do, that's the part that's not explained by me being a professor. So in that little area, if we're just looking at that part, well then, in that region, if you still see a relationship between me being brown-haired and me drinking a lot of coffee, then maybe there's still something about being brown-haired that matters. So that brings us to this idea of conditional distributions. Conditional on being a professor. Within the realm of professors, is there still a relationship between having brown hair and drinking a lot of coffee? If there is, then you can say, hey, I still found a relationship. I took out the part of coffee drinking that I could explain with you being a professor. That 2.3 cups, toss that out the window. I only focused on the 0.7. Within that 0.7, if there's still a relationship between being brown-haired and drinking a lot of coffee, well then, yeah, there's still a relationship. A conditional distribution of drinking coffee, a distribution of drinking coffee conditional on being brown-haired, already conditional on being a professor. If that's still a positive relationship, that tells you that it's just that they're professors, those brown-haired people, then that's not really what's going on. That's why we might be interested in getting a conditional distribution, because it allows us to say, throwing out that part of the relationship that's explained by something else, what's left over? And that's what is meant by the term you might have heard of, controlling for a variable, adjusting for a variable, matching on a variable, whatever it is. The idea there is that you're being conditional on some variable there, and then you're looking at whatever relationship remains, whatever conditional relationship remains within that subset of data for which you've already taken out that alternate explanation. Which is going to be very useful when we're talking about causal inference, because we know that if we're looking at the relationship between two variables, there's going to be a lot of reasons why those things are related to each other, things that are not causal in nature. So to use the example again, if you look in the data and you observe that people who wear shorts are much more likely to eat ice cream, well, why is that? Well, it's probably because that happens to, both things happen to happen on the hot days of the year. So if you looked in the data, you said, it looks like people who wear shorts are more likely to eat ice cream. And you would say, I think that there's a causal effect. Making people wear shorts will make them eat more ice cream. And then somebody would come along and say, no. It's probably just that it's a hot day, right? Conditional distributions, controlling for a variable comes to the rescue. We would say, okay, fine. Maybe it's just that it's a hot day. So we will look at the value conditional on being a hot day. We're going to split up to hot days or not hot days, or we're going to look at all the different values of temperature that it could be. We'll see what we can explain with temperature, and then we'll take the residual. So then, after we've accounted for the part of ice cream eating that is explained by it being a hot day, and the part of shorts wearing that is explained by it being a hot day, if we just look at whatever was left over, is there still a conditional relationship between shorts wearing and ice cream eating? If there is, then you can say, yeah, it's not just temperature, it's actually those two things are still related to each other. Maybe there is a causal effect there. And if there's not, then you say, oh, well, I guess you were right. It is just temperature that explains the relationship between these two things. And that's what we can get by looking at these conditional distributions. How can we actually get a conditional distribution? Well, one way is just to do what I literally just said. Use any of the relationship explaining tools that we've already talked about. Could be line fitting, could be taking means within bins, whatever it is. Explain what you can with one variable, and then take out that explanation. Whatever's left over, that residual, that is going to be our first condition, right? We've conditioned on one variable, we've controlled or adjusted for that variable, and we're just looking at what's left over. Within that leftover variation, then you look for the conditional relationship again, and that is your conditional relationship. This is much easier to do if we're talking about ordinary least squares or linear regression. In that case, it can perform this whole process for you by just adding more variables to your regression model. If instead of just regressing y on x, you instead regress y on x and z, the coefficient on x, the slope on x that it estimates for you, will be the conditional relationship. It will be the conditional relationship as the value of x changes. How does the conditional mean of y change? Conditional on z. It will do that sort of subtracting out of the explained part for you. So, conditional on different values of z, accounting for the relationship between y and x that is driven by z, looking at what's left over, is there still, as we increase x, a change in the conditional mean of y? Are x and y still related to each other, conditional on the values of z? And so we can do that simply by adding more predictors to our ordinary least squares model. We can see how this all works here. So here's some data. We have three sort of axes going on here. We have y, we have x, and we have z. And what we originally start with is that the relationship between x and y that you see there has some elements of z in it. Right? Z is explaining why those two things are related, because z is positively related to x, and it's also positively related to y. So what we can do is we can take out the part of that explanation that is due to z. So if you look over here on the right, we can see that there's a positive relationship between y and z. So we take out the part that's related to z. We do the same thing down here in x and z. We look at the positive relationship and we flatten it out. We're just subtracting out that variation. Whatever we have left over, that is the part of the xy relationship that is not due to z. You can see there's no way that z can do anything there because there's just flat lines with z. As you move z around, there's no longer any relationship between what's left over in x and what's left over in y. So to give an example, last time we looked at the relationship between the proportion of people who use vitamin E and what their body mass index is, and we found the intercept of 0.110 and a slope of 0.002. So a 1 unit increase in BMI is associated with a 0.002 increase in the proportion of people who take vitamin E. But we can think of a lot of reasons why there might be a relationship between these two things. Maybe age is a factor. Maybe older people tend to have higher BMIs, and maybe they're also more likely to take vitamin E, and maybe gender has an effect. Right? So let's put those two in as additional controls. By simply adding them to my regression model, the coefficient on BMI changes to 0.001, which is telling us that, yeah, part of the relationship that we had between body mass index and taking vitamin E is explained by what we just conditioned on, age and gender. But we still have some sort of relationship remaining. There still is as we increase BMI by 1 unit, conditional on age and gender, we still see that a 0.001 increase in the conditional mean of vitamin E. So we have taken out part of the explanation, the part of the BMI vitamin E relationship that is explained by age and gender. We've taken that out. We still have somewhat of a relationship left over in the data that we still have. And that's why we add control variables, to do that conditioning process. And that's how we can get an interpretation here, right? We still have the relationship between two variables conditional on some others, which is going to turn out to be very handy once we get more into causal inference, which is what we're about to do, because the next set of videos looks at identifying causal effects and the whole process of identification. Hope to see you there. Bye-bye.